Searchers and seekers of general truths. In this video, I will present and discuss two theorems. We will prove them at a later time, prove them later, but I want to at least discuss what they mean and what they are saying here. Okay, so let's start with the first one. If one chord is a perpendicular bisector of another chord, so that means there's two chords involved here. So let's say I have a chord A, B, so A to B. And then I have another chord that is a perpendicular bisector of the first chord, so CD. And remember, perpendicular bisector, perpendicular means 90 degrees, and bisector means to cut it in half. Okay? So if CD cuts AB in half at a 90-degree angle, then the first chord is a diameter. And when they say the first chord, it's the one that's doing the bisecting. Okay, so it's the chord that cuts the other chord. So that means if I draw two line segments inside of a circle and one of them cuts the other in half at a 90-degree angle, then the one that's doing the cutting must be a diameter. So then we're saying that CD is, or it must be a diameter if that picture is true. If that picture is accurate, then CD must be a diameter. Okay? If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So this is saying the same thing, the reverse direction of this. Okay. All right, one more theorem here. Oh, and we should name this theorem as well. This first one we'll call it diameter perpendicular bisector. Okay. So that we don't have to keep just referring to this as that one theorem. So the diameter perpendicular bisector. Okay. All right. So let's move on to one last example here. One last theorem, I should say, before we get to the examples. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So this is saying equidistant from a point. Okay, two chords are congruent if and only if they are equidistant from a point. So let's say I have a center here, and then I have a chord, we'll say CD. But what does it really mean to calculate the distance between a line segment and a point? Okay. Well, if you recall, that means the distance between a line segment and a point is the segment that's perpendicular to the segment through the point. Okay? So that's this red line here is the distance between CD and Q. Another way we can phrase it is that it's the shortest distance between CD and Q. And now let's say I have another line segment that looks something like this. And let's call this E and F. And once again, the shortest possible distance would be the one that's perpendicular to the line segment. Okay? So what this theorem says is that, and I guess we'll call these points of intersection here, these perpendicular points here, E, F, A, and B. So those distances there, they are the same if the chords are the same. So EF, the arc EF, or sorry, the segment EF rather, excuse me, the segment EF is congruent to the segment CD if and only if the distance between the segments and the center, in other words, BQ, right? That's the distance between EF and the center, and AQ are congruent. Okay? So this picture is not drawn to scale, so it doesn't look very good, but that's why this is a conditional statement. The two chords are the same length if and only if their distance to the center is also the same length. Right? So now this video combined with the previous ones, we have established 3 theorems in this section. Make sure you know what those theorems say and how to apply them. In the next section, we're going to use them to solve a few problems. As always, thank you for watching, keep working hard, and have a